Hi, my name is Corey Gully, and I am a technical specialist with Autodesk Simulation. Today what I'm going to do is I'm going to take you through the Nastran in CAD environment to show you what it's like as a day in the life, to look at some specific examples, some advanced type of capabilities we have like dynamics and linear statics, and see how they apply in an early design process. So the webcast, probably around 30 minutes, I would say. And I'm going to go through a number of things in addition to showing you the Nastran in CAD environment. Why do we simulate? What are the benefits of using simulation? We're going to look at the Autodesk simulation product offerings, what we have in terms of different tools to analyze different types of analyses. And then three specific examples that we'll cover inside of Nastran in CAD. We'll cover a linear statics example, which is most basic, but it does give you a lot of benefit and a lot of good information up front. We'll look at a vibration example, looking at modal analysis. And then we'll also take a look at an example of a more advanced type of analysis called a nonlinear dynamic analysis, or a nonlinear transient response, as we call it inside of Nastran in CAD. So why do we simulate? Ask ourselves a very simple question. We simulate so that we can identify behaviors of our structure up front and early on in our design process so that we can identify fatigue failures or stress failures. Take a look at an example of this helicopter. This is probably an example of someone that didn't use simulation. What's happening here is a phenomena called resonance. And what's going on is the structure natural frequency is matching up with the natural frequency of the blade, leading to excessive displacements. If you were to use simulation, you wouldn't expect this type of failure. We could target this on early in our design phase so that we don't waste prototyping time or put out fires towards the end of production. So simulation used to be an afterthought. It used to be something where early in the design process, we would go in, we would analyze our structures after we had made our design. So what's actually changed throughout the years is simulation now is being brought on earlier in our design process. The reason that's happening is because if you think about it, there's less risk involved if I put more time and effort into analyzing my structure up front. I'm not fighting against production schedules or anything like that, or having to go back to square one, if I've already made my designs and then I simulate. If I simulate early on, I can make sure that when I get it to production, I can make sure I've got a final optimal design so that I can meet that production schedule and I don't have to restart any of my designs. I really like this slide. This talks about some of the specific benefits that you get using a virtual prototype versus a physical test. Kind of goes without saying, but a physical test is what? It's very physically intrusive. They're hard to set up. They take a lot of man hours, a lot of time. Time is money, all that sorts of things. But if you think about it as well, there's also some additional parameters that you might not think of. With physical prototyping, we're limited to data to the specific sensors that we set up inside of our physical model. Now, with a virtual prototype, we could set these up much more quickly than a physical prototype. And then going back to the data information, we can receive information anywhere inside of this model. So if I run an analysis, I can pick anywhere in the model and retrieve instantaneous information. I don't need to place any sort of sensor in that region. The entire model has inherent sensors built in. So that allows me to retrieve valuable information everywhere. And what I can do with that is I can create what-if studies, which will ultimately lead to a more optimal design. Quick napkin scratch ROI here. Should have labeled these, but the left table refers to a physical prototype, and the right refers to a virtual prototype. These are really arbitrary numbers, but just to tell the story, the first test that you run from a physical prototype is always going to require the most amount of time, the most amount of effort to set up. The hardware cost is going to be more. And then as I start to set up additional tests, the time stacks up and the man hours stack up. With a virtual prototype, now that you paid for the cost of the software, you're just paying for the cost of the analyst at this time. It's going to be a lot quicker for him to set it up. There's no hardware cost involved, and so therefore your entire simulation process is going to be a lot cheaper than a physical prototype. So from a simulation product offering standpoint, what do we offer? Depending on which tool you want to put into your tool belt, or depending on what you're analyzing for, we probably have the right package for you, or we do have the right package for you. If you're analyzing heat transfer or any type of fluid or gas, we've got a CFD tool called Autodesk CFD that will allow us to analyze that information. And speaking of mechanics, which we're here to talk about today, we're going to talk about Autodesk Nastran in CAD. That's a product that we have that sits right inside of your CAD tool. And I'll get into more of that later on in today's webcast. We also offer Autodesk Simulation Mechanical, which is a standalone product which is not going to tie up a CAD license, but can very much do some advanced type of analyses. It's also structured in right under there underneath the mechanics. Then we have some advanced materials packages. One of the most popular packages that we have is Autodesk Mold Flow, which is an injection molding simulation. And then we've got an advanced materials product that will tie into these different types of analyses called Autodesk Helios, which will allow us to understand our as-manufactured properties and understanding that advanced type of material analysis. So speaking of the mechanical simulation offerings that we have, Autodesk Simulation Mechanical, we sell that. That is a standalone product, not going to tie up a CAD license. We also have Autodesk Nastran in CAD, which we'll talk about today. It's embedded into the CAD interface. The beauty about that is that as I'm creating my designs, I can run simulation parallel to that in the same interface, and then I can retrieve instantaneous information about my design and easily just jump back to my modeling environment inside of CAD and make some quick changes. And then thirdly, we also offer just the solver for Autodesk Nastran. So over the years, Autodesk has put in a pretty hefty investment into our simulation tools. If you look back from all the way from 2005 to 2016, each of these pieces of tools that we have for you are only going to enable you to analyze for different parameters or give you some advanced capabilities inside a simulation. And I want to go through all of them, but you can see that we have put in a hefty investment there. Today, specifically talking about the NEI Nastran piece. So now that we've gone through some of the offerings that we have and looked at some of the benefits of simulation, let's get into more of a day-in-the-life scenario when we're talking about Autodesk Nastran in CAD. And I like to start with linear statics. And the reason I start with linear statics is because it's the first analysis that you run always. I don't care if you're Boeing or if you're NASA, the first analysis that they run is linear statics. The reason that they do that is because it provides me with valuable information up front about my design without the need to run more computationally expensive types of analyses. I'm going to retrieve all this information up in linear statics, make my design changes, and then proceed forward. And what it actually is going to tell me is it's going to tell me how strong my design is. How does this actually behave under any given static load? So let's pretend we're going to take a nice boat down to the lake one day, and we're going to analyze the trailer hitch. So how strong is this trailer hitch when it's towing a boat, when my truck is towing this boat? This is what we're going to simulate, and I'm going to show you exactly what that process would look like inside of Nastran in CAD. Now, the first thing that you'll notice is I'm sitting right inside of a CAD tool. I just need to go up, and I need to turn on the environment for Autodesk Nastran in CAD. The beauty of this is the left side will show me all of the feature information, everything that I set up, and the top is a very ribbon type of layout that shows me all the tools that I can put in. All I have to do is give it a name and define the type of analysis I want to run. So depending on what you're analyzing for, we can pick the different type of analysis that we need to run for our trailer hitch. The first thing that you do in any analysis is we define a material. In the case of Autodesk Nastran in CAD, what we have is an idealization. What this is going to do is it's going to allow me to group materials to specific bodies inside of my analysis. This will end up allowing me to go in and group these together in an organized fashion so that I can go in and I can easily see this. So not only am I applying materials, but I can also choose different element types and things like this. So let's say that the ball and the pin are made of stainless steel, and then the housing may be composed of a different type of material. So I can use the quick access toolbar there, and I can grab the particular material I want to use. And let's say that's made out of a carbon steel. So over on the left-hand side of my tree, if I need to ever go over and update that information, it's clearly laid out for me in a visual format. Now think about how this is actually loaded up. It's going to be loaded up with a constraint, which is a fixture, which might be tied to the back of my truck. And then I could say it's completely fixed there on the back face. The other thing I need to do is I need to define a load. This is going to be the load that comes from the boat. So if I make my way from left to right on my ribbon, I can pick the particular component where I want to apply that load. And the beauty about using an in-CAD tool is even if you have a weird load direction, you can use CAD geometry or any sort of reference geometry to define the overall direction of that load. So I'm going to use the housing there as a direction for the load that I'm going to apply. The next thing we need to do is define our contacts. This is going to tell the bodies how they behave or how they contact one another. The nice thing about Nastran in CAD is it will actually create multiple contacts. So if I need to go in and I need to edit any of this information, I can pick on the individual contact that was created and I can choose a new type of contact for that analysis. The last thing that we need to do inside of any simulation is to define a mesh. So I'm going to define a mesh size for the bodies that I have in here, and I can go in and I can look at the mesh for any given body that I have. So I've already set this up, so I can go ahead and I can load my results, which is one of the beautiful functionalities that we have inside of Nastran in CAD. And then I can define individual plots that are either created for me automatically, or I can go in and I can start to change this information up front. The first thing that I like to look at is the displacement. The displacement tells me how much this is going to move for any given static load in a linear statics environment. I can also use that pre-populated template to go in and specify an additional type of result that I want to look at. Say I want to look at von Mises stress, which is usually used for a particular fatigue failure to let me know how I am or how strong my design is before it's going to enter any type of plasticity. So I can see how strong it is. I can compare that back to the yield strengths of my components. I can easily use the quick drop-down selections from the window that was new in Autodesk Nastran in CAD 2017, and I can pick different types of behaviors as well, like safety factors, and I can even look at the reaction forces on the nodes that I have in my model. So let's talk about an additional type of analysis that we might run. So let's say now we're going to look at a vibration type of analysis. So this is going to be different from a linear statics example. Vibration is going to let me know, if I'm going to resonate at all. I want you to think back maybe to the high school physics class that you took, and you might remember the tuning fork that you used. And what you did is you took a tuning fork and you basically slapped it, and it liked to move and it liked to vibrate at certain frequencies. Well, those vibrations are called natural frequencies. They're the frequency at which the structure is excited based off of the overall geometry and the stiffness of that geometry. And the shape that it likes to vibrate at, we call those mode shapes. Now, those are two things that you're going to get when you're using a modal type of analysis. It's important to understand this behavior because this behavior can help us understand whether we're going to lead to fatigue or, like the helicopter, fatigue out or high stresses and displacements. We're going to be able to observe for that resonance phenomena. So let's take a look at how that looks inside of Nastran in CAD. Now, the nice thing about Nastran in CAD is I don't need to redefine this information. I can easily duplicate my analysis, and I can define this as another name, and it's going to copy all the information from one study over to the other, so I don't have to take the time to redefine that. I'm going to analyze for a new set of parameters, so I'm going to choose normal modes to allow me to understand the vibrational characteristics of my structure. The only additional parameter I have to put in here is the number of modes, or the number of excitation frequencies that I want to look at in my structure. Once my analysis is done, I can see the mode and I can see the frequency inside of the plot, and then I can animate that particular frequency to look at the mode shape. So I can go down for any of the 15 that I've added in this particular example, I can look at those characteristics. Now I want you to think about how this could tie into resonance. Let's say that the natural frequency of the structure was around the operational frequency of our structure. What would happen is the phenomena called resonance. In this case, our first mode was at 480 hertz, and then we saw that mode shape move up and down. What we could do inside of an in-CAD environment is if I needed to move that outside of the operating range, I can easily jump back over to my modeling environment, and then I can put a stiffening rib there and stiffen up my structure so that I can move that first natural frequency out to only stiffen it up so I don't observe any resonance phenomena. So that's one of the benefits that you get whenever you're going to look at this particular type of behavior. So let's look at another example. Okay, so we've talked about linear statics, looking at how strong it is. And we've also looked at, or from a static standpoint, seeing how strong it is. And we've also looked at vibration or modal analysis, allowing us to understand how close we are to resonance. Do I need to stiffen up my structure? What does that first natural frequency look like? Am I going to run into any operational frequencies? Now let's play out another scenario in our head. We're not going to apply the load slowly anymore like we do with linear statics, but let's say we're going down the road and the car in front of us just suddenly stops and I have to slam on my brakes. What is the behavior of that trailer hitch? Well, now we need to account for time. We need to put this into the time domain. Because that load is no longer being applied slowly, it's being applied very quickly, like a shock load. So the dynamics are actually going to be able to bring in inertial calculations into our analysis, and we're also going to be able to account for time. And if you think about it as well, when we're talking about the world of nonlinear, the load itself is nonlinear with time, right? I can change that with time. But what if our structure might have passed our yield point? Well, then we're entering a plasticity type of behavior. Plasticity is going to change my material characteristics. Once I pass that yield point, my structure is actually going to stiffen it up. It's going to become less ductile, and we're going to have new behavior. So we can account for that inside of here as well when we're talking about any type of nonlinear analysis. So inside of Nastran in CAD, I could easily duplicate this information just like I did for the normal modes analysis. And what I'll do here is I can change some of the parameters. So with the dynamic setup, I can define a length of the analysis. So I could say, hey, this is going to last for a few seconds, this is going to last for half a second, etc. The other important piece of information I can put in here is the damping information. So I can put in a modal damping value for my structure, and I can also put in the dominant frequency, which is the first natural frequency of our structure from a modal analysis standpoint. So for a load that's going to change with time, I'm going to use a table to define the characteristics of that load. So I'm going to apply the load very quickly, and then the load is going to be released. And then what should happen is dampening effects should dampen out the system. So that's the one change that I need to make when I'm talking about a transient type of analysis. Now when it comes to the material, I'm going to turn on nonlinear effects. So let's say I'm assuming that I'm going to pass my yield point. Now all of a sudden my behavior starts to change. So I need to be able to account for that by running a nonlinear type of analysis. So I'll choose the particular nonlinear material information, which is going to allow me to put in a bilinear stress strain curve. I can choose the material for my housing. I can turn on those nonlinear effects. Now when I go in and I look at my results, I can do the exact same thing. But what you'll notice up here in the subcases is I can choose any instance in time where I want to observe that particular type of behavior. I can also look at displacements and stresses for any specific given point in time because of the transient effects. The other thing that we can create inside of, or the other feature that we can create inside of here is a plot. This will show max displacement versus time. We can see we get our peak stress, and then our system is going to start to dampen out with time. So we can observe that maximum displacement, and it allows me to understand if I have any plastic deformation in my system. Now, if you want to observe the overall behavior of our structure, we can create a multi-set animation. This will allow me to create that plot versus time. And remember what's actually being simulated here. You're going to see a large displacement, and then all of a sudden you're going to see some smaller displacements as this system starts to dampen out. You could take this animation, save it out, send it as an AVI file over to someone that might be interested, maybe management if they want to see how the structure is behaving, or an engineering manager. But I can go ahead and I can observe this behavior because of that. So let's play out another scenario. So let's say the engineering manager, now that you've passed this information over, says, you know what, the displacement was a little too large. I need to reduce the overall deformation inside of my design. Well, simulation is no longer an afterthought. It's something that we're putting on earlier in our design process. We're investing a little bit more time up front so that we can create this optimal design. The beauty of CAD is it allows me to easily go over to my modeling environment, take this information, make the updated changes based off the behavior that I'm seeing inside of simulation. So let's take a look at how we would how we could make design changes inside of our CAD environment, reflect those over to simulation so that we can create a more optimal design. Now, whether you're working inside of Inventor or inside of SolidWorks, we work with both. But the first thing I noticed whenever I looked at my results is the maximum displacement was really due to a lack of stiffness that I had in this vertical direction. So what I may do here is I may go into the CAD environment and I may go in and add some sort of stiffening rib so that I can stiffen up that particular direction and reduce that overall deflection so that I can come up with a more optimal type of design. You can use part configurations inside of Inventor, or you can use configurations inside of SolidWorks. You can create an additional type of configuration with different geometry that may differ from your CAD information so that you're not changing things, or even if you want to run a what-if type of scenario, this gives us the ability to do that. So I'm just going to add that to the particular type of simulation that I want to run, launch back into our simulation environment, and because I've made some design changes, the only thing that I have to do is I have to recreate my mesh information here. So I can duplicate the analysis, tie it to the particular configuration that I've run, go in, and I can recreate the mesh for this individual model, and then we can look at our updated results. So now we look at our results. Let's say that we wanted to reduce that deflection to under 1/8 of an inch. We're sitting at about 0.1178 right now as a maximum deflection. We can easily use these flags to call out the maximum and minimum deflections that I'm seeing inside of my model. And I can also look at other behaviors as well, like stress, if I wanted to go in and see how close I am to that particular yield point, make sure that I'm not passing that yield point. If I am and I want to observe a worst case loading scenario, I might go back in and tie in a nonlinear type of model. So let's summarize. I went over quite a bit of information there. So what we did is we took a CAD model, we went in and we analyzed first linear statics. Linear statics understood how we were going to behave, and then we looked at additional characteristics like vibration to avoid resonance. We looked at a worst case type of loading scenario, which is a nonlinear transient type of scenario where I can change the load with time. and observe that plastic behavior. The beauty of this was being able to take all that information and make an informed design decision inside of Nastran in CAD, jump back over to my CAD modeling environment, make those quick design changes for a more optimal design. And what this does is it improves my time to market, because no longer am I going all the way through my design cycle, making changes, and then having to go back to square one based off the information that I'm seeing. I have all that information tied in up front so that when I get to the end of my analysis, or when I get to the end of my design, it's already been analyzed for. This allows me to create all those multiple what-if analyses to come up with that more optimal product. So I want to thank you for joining today's webcast. My name is Corey Gully. Again, I'm a technical specialist with Autodesk. If you have any questions, please feel free to send me an email at corey.gully@autodesk.com. Thank you.